Hi, my name is Adam Noel, and welcome to my seminar on Molecular Communication Essentials, Building Blocks for Analysis and Simulation of Diffusion-Based Systems. This is a pre-recorded video, but I do look forward to engaging in the live Q&A after this session is broadcast. And if there's an opportunity for me to engage during the broadcast through a chat functionality or something similar, then I do hope to take advantage of that as well, if any questions do come in. I've structured this talk to be very much at a tutorial level, and it does have three main parts. So after my introduction, I'll have a section on deterministic reaction-diffusion systems. This part of the seminar might have a fair bit of similarity with some of the other talks, but I think it's good to reinforce and go over some of these concepts. The second part of my talk will be showing how we go from a deterministic representation to a stochastic representation, including a discussion of the most relevant random variable distributions. And then the third part of this talk, which I think might be most interesting, I'll be going over some of the details of actually implementing simulations and going over some pseudocode that you can use for putting together your own molecular communication simulations. I'll finish off the talk talking about some existing simulation platforms that you might be interested in checking out. First off, a little bit about myself. I'm on the steering committee for the symposium, MBCom. So on behalf of the steering committee, I'd like to welcome you once again and thank you for being involved in this first event, and we hope it's the first of many to come, even in this virtual format. I also serve as the secretary for the IEEE Communication Society Technical Committee on Molecular, Biological, Multiscale Communication. As you may be aware, this technical committee has endorsed this event, and I do encourage you all, if you're interested in being more involved with this research community, is to sign up for our mailing list, which I give a link here. Hopefully the slides can also be provided separately so you can easily follow and see this link afterwards. You can sign up for our mailing list to get more information about the events and activities that our technical committee is involved in. Personally, on the research side, I've been involved in molecular communication research since 2011, so I hope that gives me some credential for being able to speak here today on this very interesting topic. I do want to acknowledge some of my collaborators. Apologies if for missing anyone, but I've tried to list those here who I work with most closely involving the topics that I am actually going through in this talk. So first and foremost, my PhD co-supervisors, Robert Schober and Karen Chung. I also work with a number of current and previous PhD students in Robert's group, including Arman, Fahid, and Vayan. While I was doing my postdoctoral work, in particular, I was working with Professor Dimitrios Mikrakis and Professor Andrew Eckford, both in Canada. And during this period, I was also working with Nan Yang in Australia and two of his students, Yuting Fang, who's now graduated, and Yiran Wang, who was also graduated with a master's. And finally, Yanshu Deng, who's at KCL, who's also speaking this week. Actually, you might have recognized a few of these names here because Robert, Nan, and Yansha are all speaking today. So I've tried to structure this talk to not overlap their talks too much because I think they'll be talking about some of our joint work as well in their presentations. But yes, the content I put together for this talk includes work with all of these people. So ultimately, since I've gone in the direction of trying to make a tutorial type video, I've tried to design this lecture so that by the end you'll have the tools that are needed to design a simple diffusion-based channel model for communication, to understand a statistical description of reaction diffusion, and also to implement basic algorithms for simulating molecular communication. So basically, I'm trying to give everyone kind of a common foundation level to be able to develop an end-to-end channel model and perform simulations from scratch. So this might be a bit ambitious for a single video, but let's see how far I get today. I'm going to give a target system that I'll sort of be referring a lot to and kind of thinking of when going through a lot of my examples. And that is a system where we have kind of an open environment with a single transmitter, which is a point Tx listed right here, and a single receiver, so one Rx right here. And this particular image, it's shown here as a sphere, and but really it could be any shape in general. The receiver will be counting molecules that are released by the transmitter. So at the moment, colored two molecules that are inside the receiver are red, and all the other molecules that are moving around are currently gray. But also, this target system could include one or more chemical reactions that these molecules are able to participate in. So this is sort of the target system that I'll be working towards and referring to throughout this video. I want to draw attention to two particular key references that include a lot of the ideas that I'll be covering in the talk today. So one was a survey that we published in 2019 with Robert and a few other members of this group. So this was on channel modeling for diffusive molecular communication, a tutorial review, perhaps suitable, a suitable reference for a tutorial video today. But I also want to mention a paper that presented a simulation framework, which I won't actually talk about in detail until the very end of this video, but a lot of the ideas on implementation I will be covering today. This is a paper simulating with a chord actor-based communication via reaction diffusion. This paper was published a few years ago. So these two papers really are the most relevant. I'll be referring to other ideas and results that do come from other papers. I'll be trying not to do too much self-promotion in this video. But I do want to draw attention to these two specific works. And if you're interested in reading even more, you can find lots more details on my website, which I do link to at the end. Okay, so now we can go into part one. So this first part of the tutorial is going to be covering deterministic reaction diffusion systems. And just to give a bit of a motivation for why we're interested in deterministic reaction diffusion systems. And this is worth doing because the behavior at a micro scale of molecular phenomena can often be quite noisy. And it's actually the noisiness that we're most interested in as communication researchers, because if the signaling was perfect, then we wouldn't have anything to do. There wouldn't be any communication work that is necessary. But it's important to start with, or it's very useful to start with, a deterministic perspective for modeling. So with this approach, we're going to be assuming that our molecule concentrations are analog, so they're continuous and can take any real non-negative value. So as we see here in this graph, and I'll be referring to this image quite a few times, but this is a plot over time, really over arbitrary units, and we're counting a number of molecules at our receiver. And we have this continuous curve. So it's continuous time and it's analog in value. So it can take values that are even between, let's say, discrete numbers of molecules, when really if you're counting molecules you should only have an integer number. But in a deterministic approach, we're considering analog concentrations. This approach is useful because it facilitates a lot of the mathematical modeling, and it's actually a key part of the stochastic interpretation. So we need to start with a deterministic to give us important information that we need to know to understand the statistical behavior of these systems. With that being said, if your system is on a sufficiently large scale, a deterministic approach can actually be quite accurate. It really does break down when you get down to, let's say, a countably small number of molecules in your system. But if you're dealing with very large molecule concentrations, then a deterministic approach can actually be quite accurate. So we're going to use this as our first direction in this talk today. So the objectives that I have in this part of this video is to cover the workflow for deterministic channel modeling. And this is going to begin with discussing differential equations. In particular, I'll be focusing on those that are relevant for reaction diffusion with a flow component. I'll be talking about how to represent system input and output with boundary conditions. And at the end of this part, we'll be looking at some closed form solutions, and these can be used to describe a channel impulse response. So ultimately, our aim for this part of the talk is that we wanted to be able to describe the concentration, which is this variable C. It is a variable of position D and time t. And what we want to do is identify either expressions or a methodology that will let us know and describe what this parameter C should be. So to begin this discussion, we'll jump into Fick's laws. Alfred Fick proposed these laws in the 19th century. He was doing some experiments. I believe it was looking at pollen moving around in a glass of liquid. And he noticed sort of this randomness of these tiny particles that were moving around in the water. And so he came up with a few laws that were describing the motion of these particles. So they seemed to be moving around randomly, as far as he could tell, but there were certain trends mathematically that he used to describe this motion. So these are known as Fick's laws. There's a Fick's first law and a Fick's second law. We'll actually find the second law to be more useful for our immediate purposes. But the first law is to say that the diffusive flux J, and so this is a function of position D and time t. And this flux is something that scales with the diffusion coefficient, which are right here as a constant D, and a gradient of the concentration. So the concentration is also a function of position and time. But essentially, this is using flux to kind of describe a net local change in concentration at a given space and at a given moment. A bit more relevant, though, is Fick's second law. This gives that the rate of change with respect to time of the concentration is going to be equal to the diffusion coefficient multiplied by the Laplacian of the concentration. And the Laplacian is just a second-order spatial derivative. So this symbol here is equivalent to second-order derivative with respect to x plus a second-order derivative with respect to y plus a second-order derivative with respect to z. But essentially, this expression right here, Fick's law, can be used really as a starting point for a lot of the deterministic expressions that have been developed and which are used in molecular communication research. To elaborate a bit on the diffusion coefficient itself, so the diffusion coefficient D, this describes the variance of molecule spreading. If you have one-dimensional motion, then over some interval t, this one-dimensional motion will scale with the square root of 2 times d times t. And if you have multiple dimensions where your molecule can move, then you get this the same scaling along each dimension. And the essential idea of where this diffusion comes from, basically what we're looking at is we're considering some large molecule that's inside of a fluid. And this fluid is made up of a solvent or some other very large quantity of molecules. So let's say we're interested in this red molecule here. And this red molecule is surrounded by much smaller blue molecules. Let's say it's water or something similar. The concentration of the blue molecules is much, much higher, and these molecules are all moving around. And so they're having these collisions. So because of these collisions, our molecule of interest gets bounced around a lot. And we can sort of abstract away the solvent molecules and just consider our molecule of interest, and if we were to track its trajectory, it would look like some kind of random walk. This is because of all the large number of collisions that are taking place. Now, it's not quite random. If we knew the position and orientation and kinetics of every individual solvent molecule, then it would be possible to derive what the trajectory of this larger molecule of interest would be. However, in practice, we don't have this kind of information, so we effectively treat it as a random effect. Nevertheless, the notion of the diffusion coefficient D is useful for a deterministic representation. There are a few underlying assumptions that we take when we're applying a diffusion coefficient. We usually assume that the temperature and the pressure within the fluid of interest are both constant and uniform. We usually assume that we have a low molecule concentration, in particular relative to the solvent. So we assume that most of the collisions that our molecules are participating in are with molecules that are not the molecule of interest. They're with kind of the background molecules in the solvent. There are actually some special cases where you can actually calculate D based on the physical parameters. But this tends to be under very special cases, which also apply additional assumptions. So these days, it's more common to just assume a D and not assume a particular expression for D to be used. Although they can be useful to get kind of an order of magnitude idea of what sorts of parameter values your diffusion coefficient might take. But for our intents and purposes, we'll just be assuming that we have a constant diffusion coefficient D. So simple advection. In practice, fluid environments tend to have some kind of flow. This could be a bloodstream. This could be a microfluidic channel in some kind of lab on a chip system. This, on a bigger scale, this could be air currents. So a fluid could be a liquid or it could be a gas. A fluid doesn't have to be a liquid. And it's certainly possible for molecules to diffuse in air. It's just in air, especially, you tend to have a lot of underlying currents or flows that are taking place that are able to influence molecule propagation. In this work, we'll represent flow with a fluid velocity vector v. And to simplify things in this video, we're going to assume that our flow is constant across time and space. So we can assume that v of d and t is just equal to v. What we're able to do is we're able to include a velocity component with fixed second law. So we're able to write an advection diffusion equation which starts with fixed second law. So we have the rate of change of concentration over time and space. And that's equal to the diffusion coefficient multiplied by the Laplacian of the local concentration minus a gradient of the velocity times the local concentration. And this is useful for, this enables us to include velocity in a deterministic model for molecular diffusion. Next up, I want to mention chemical reactions. So chemical molecules, they interact with their surroundings by reacting, so engaging in chemical reactions. I'll be covering some reactions in a fair bit of detail, but just to give you some examples right now, reactions of interest could include synthesis, so a reaction that creates a molecule, binding, which is a reaction where two molecules collide and bind together, or one molecule binds to some kind of surface. And also an interesting reaction is degradation, where one molecule breaks down or is broken down by other molecules. If you haven't covered a whole lot of chemistry, just to give you a very quick summary, that the reactants in a reaction are your inputs, shown right here, and the products are the outputs, so we have products. So as a very simple reaction, we could have, looking at the formation of water, this is not how water is actually formed, but just to create a reaction out of its components, we can say that two hydrogen atoms and one oxygen atom, these collide together to give H2O, or water. It turns out that many biologically relevant molecules are released or they are captured via chemical reactions. So there's a lot of interest in biochemistry and understanding basically the network of reactions that are used to drive a lot of interesting biological behavior. And so it's useful to include those in in our modeling for a molecular communication system. Elementary chemical reactions are a way of breaking, or when you take a potential reaction and you break it into its elementary steps. This provides an exact description of what molecules are involved in each step of a reaction. So instead of including your initial products and then, your initial reactants and then the products you have at the end, there could be a number of steps that take place, and each of these transitions in its simplest form can be represented as an elementary reaction. So the possibilities of elementary reaction are 0th order, and these are when we have no reactants whatsoever, and we end up with a creation of products. Now generally this is an approximation because we don't have spontaneous creation generally. But if we have a reaction where there's a very large bulk of a reactant and we can approximate the creation of the product as being a process whose dynamics doesn't change with time, then it's possible to represent it as a 0th order reaction. A 1st order reaction has one reactant, so we start with some kind of reactant and then it reacts, so either through conversion or some kind of degradation, and we end up with one or more products, or even 0 products if it's just a degradation reaction. 2nd order reactions have 2 reactants, so these are collision-based. So we have 2 separate molecules that when they collide in the right orientation and with enough energy, they're able to react, and then they provide some series of products that could include some of the same molecules, or could include some kind of degradation or just binding, or lots of other options as well. It's also possible to have higher order elementary reactions, but these are rare, especially since they need to require a higher number of molecules colliding with the correct orientations and energies in order to trigger a reaction. But you will see quite intuitively here that the labeling of the order is is determined by the number of reactants in a reaction. So it's quite easy, if we know that we're looking at an elementary reaction, to determine what the order of that reaction is. And this is useful because each of these different orders are implemented in different ways, especially when we look at simulations, and we'll be seeing that later in this video. Just to give you some biological examples of these reactions, I've chosen a representative biological environment where we see examples of all 3 of the orders that I discussed. So what we have here is a diagram representing the neuromuscular junction, and this is essentially a space between a neuron and a muscle cell, and neurons are able to send signals to muscle tissue in order to trigger muscle contraction. So all of our motor movements of our body are controlled by signals that are sent from neurons to muscles. And when we have this space in between a neuron and the muscle is called a cleft here at this neuromuscular junction, and we have molecules that are released at the neuron side. And these molecules are able to diffuse across this space, which is only about 30 nanometers in size, and they're able to bind to the receptors that are here on the postsynaptic cleft surface. And when you get sufficient molecules binding, it's able to trigger a muscle contraction. So to apply the elementary reactions that we've discussed, we have 0th order. This can be used to approximate the molecule release by the neuron. 2 reactions here that are 2nd order, or which we could also approximate with 1st order reactions, include these molecules binding to receptors. So we have diffusing molecule, and we have receptor. So this would be a 2nd order reaction, but we can also approximate it as a 1st order reaction by being a molecule just hitting a surface. And second, we also have a degradation reaction that occurs here in order to help clean up this channel. So because these molecules could hang around for a long time, there are processes in place where there are reactions molecules that bind to these signaling molecules and then break them down so that they can be recycled and returned back for later reuse. This type of degradation reaction is also second order and can also be approximated as a first order reaction. So chemical kinetics describes essentially the dynamics that are involved in chemical reactions that progress. And the convenient thing about the elementary reactions is that these directly correspond to the relevant chemical kinetic equations. Now, we've already seen that reactions, these consume reactants and they create products. The reaction rates that correspond to a reaction only depend on the reactants. They don't depend on the products themselves. So I should note that zeroth order reactions, they tend to have what's usually a constant reaction rate. Conveniently, we can also take multiple reactions that occur simultaneously and we can combine them together within a single kinetic representation. So to kind of go over these ideas and jump immediately into an interesting example, I talked in the previous slide about the neuromuscular junction, where we have molecules that break down our signaling molecules. Well, that's an example of an enzyme reaction, and the classical reaction representation for this is that we have a molecule A, which is our signaling molecule of interest. We have an enzyme E. These participate in a second order reaction and bind together to create an intermediate molecule, AE. This intermediate can then participate in one of two reactions. The first one is the reverse of the binding reaction. So A and E can combine with rate K1 to give AE. AE can also break down as a first order reaction with rate K-1 back into the reactants A plus E. So this reaction here is called a reversible reaction. The intermediate AE can also participate in another first order reaction with rate K2 to give us our original enzyme and then some form of a degraded signaling molecule. So this reaction here is an irreversible chemical reaction. And it's possible to kind of combine multiple chemical reactions that involve the same reactants and products using this kind of representation, where we have basically arrows going in every direction where there are reactants leading to products. To describe the kinetics, I'm going to focus on the intermediate. So we see that there are three reactions that lead to this intermediate molecule. So if we try writing the rate of change for this intermediate molecule, we see that this molecule concentration increases whenever there is an A plus E reaction, which is according to rate K1. So the first term here in the kinetic rate is positive because this reaction driven by rate K1 includes the binding of the A molecules and the E molecules. And all we have to do is to take the product of their two local concentrations. And that will give us, when we multiply by the rate K1, the local rate associated, the local reaction rate with time associated with this reaction. The other two reactions involving the two different ways that the intermediate can break down into other forms, these are both reactions that will decrease the concentration of the intermediate that's available. So there's a minus sign associated with these reactions. They both scale with the concentration of the intermediate itself. And all we have to do is add up the corresponding rates for the individual reactants to get a net effect for the overall kinetics that correspond to this molecule reacting and breaking down into other forms. So in this example, we're able to show both second order and first order reaction influence on an overall kinetic rate. Now it is also conveniently to combine the dynamics that we just showed here with the advection diffusion equation that we showed on our previous slide. So I won't show those all together on one equation just for the sake of space and time, but just to be aware that we're able to represent all of these with a single equation for the rate of change of a concentration with respect to time. Once we have our differential equations, and we could have more than one if we have multiple molecules of interest that we're modeling simultaneously, as we would have in the case of the enzymatic expression that I just showed. But those kinetics themselves are insufficient to fully describe the dynamics. You need to have some other information about the system that you're interested in. So in particular, we need the initial conditions. So this would be the initial concentrations at time 0 of any molecules in interest that you're tracking. So basically anything involved in a chemical reaction, you need to know how much of that molecule was initially present and where it was present. In molecular communication modeling, we usually represent the transmitter as some kind of initial condition. So a place where the transmitter is, we say that there's molecules that are created at that time, at that location. But another initialization of interest is if you have some kind of background molecule, let's say, that's present everywhere, that could also be represented with an initial condition. We also need boundary conditions. So these are other times or locations where the concentration or the rate of concentration is known. So these are usually imposed by the system geometry. So for example, if you assume that your system is unbounded, so there's no outer, there's no finite outer boundary limiting where molecules can be, this tends to be represented with saying that your concentration as your distance becomes asymptotically far away. At any time, that concentration should tend to 0. Secondly, our receiver in our system might also be represented by a boundary condition if we have some kind of implied local reaction that's taking place. So instead of you having a reaction that's directly described in our differential equations, we can also imply a reaction by our boundary conditions that are associated with, that are defined at the places where those reactions take place. For solving differential equations, what we do is we need to apply the initial and the boundary conditions, and hopefully we can have, if possible, a closed form solution for our concentration as a function of position and time. And then the position we're usually most interested in is the receiver of our system. Some of the methods for solving these differential equations might include direct integration, separation of variables, as well as the Laplace transform. There's some very good classical texts that give existing solutions. So I want to draw particular attention to Karsla and Jaeger, who had the book Conduction of Heat in Solids back in 1936. And John Crank, who wrote the Mathematics Diffusion. The first version was in 1956. I think there was another version in the 1970s. I think these are both old enough to qualify as classical texts. And they're basically repositories of different ways of solving systems of differential equations. By analog, it's quite interesting that the diffusion of molecules in a fluid is analogous with the conduction of heat in a solid. So we can actually use the same equations for describing either one of those mathematically. In practice, we often try to rely on existing results when studying a new system of interest. So we try to define a system so that it matches the conditions for an existing system. Or we might even try intuition to extend results that are already known to include components to account for, let's say, additional reactions that we want to introduce. But this just to give you some idea of the kind of approaches that can be used for solving these systems of differential equations. I'd now like to apply these deterministic ideas to a couple of example systems. And they're both going to be versions of this target system that I introduced at the beginning, where we have a point transmitter at some fixed location. And in this first example system, I'm going to assume that the receiver is what we call passive. And this means that it's transparent, so there's no reactions that actually occur here. We can just think of the receiver as a is an observer that is just looking over a particular subspace of our environment. That space is not influencing the diffusion of the molecules in any way, but it's able to count the molecules that are present within the subset of interest. So this is a passive receiver. We're assuming that we have unbounded 3D space, so molecules that get released by the transmitter and diffuse around, we assume that these can go as far away as they want. They don't participate in any reflections or any other reactions. We assume we don't have any reactions occurring anywhere, and that we also have no flow present. And in terms of initial conditions, we're assuming that our transmitter releases an impulse of molecules at time t equals 0. So at time t0, the transmitter creates a number of molecules at the point where the transmitter is, and then it allows those molecules to diffuse away. So this is a relatively simple system, and the only differential equation that we need here is the one for diffusion, so we just need to use Fick's second law, which we've already shown. The point concentration in this particular case is quite well known. This is a bit of a classical example, and it's described by this expression here. This is, we assume that the number of molecules released by the transmitter is equal to n, and so the concentration at any point is going to be equal to n divided by 4 pi dt to the power of 3 over 2, multiplied by the exponent of negative distance from the transmitter to the center of the receiver squared, divided by 4 dt. It's possible to take this expression and you can validate it by taking the derivative with respect to time, taking the second derivative over space, and you can see that then that both of those will be equal. So you can leave that as an exercise if you'd like to convince yourself that this expression does satisfy this differential equation. As I noted, this is a point concentration, so it's also of interest to determine what's the actual number of molecules that you'll receive within the volume of a receiver, not just a point concentration. So there's two approaches that are possible. One is to integrate this expression over the volume of your receiver. A second approach is to just assume that in the local area where the receiver exists, that your concentration is going to be uniform. So it's going to be a constant value over the entire receiver, and then you can get the number of molecules by just multiplying the point concentration by the volume of the receiver. And this approximation is accurate when you're sufficiently far from the transmitter. Just to elaborate a bit on this analysis, so method 1 where we apply an integration over the volume, just to give you an example for the case when you have a spherical receiver, you get this expression here for the number of molecules as a function of time. And this is an expression that has two exponentials and has two error functions, which are basically integrals of exponentials. In this expression, the lowercase r is the radius of the receiver, and this constant d0 is just the distance between the point transmitter and the center of the receiver. So even though this is a relatively simple case, we still end up with a relatively complex expression. So for analysis, we tend to favor applying a uniform concentration at the receiver if we can. So this would be method 2. So all we need to do is take the point concentration and multiply it by the volume. And this sort of approach tends to be much more commonly used in the literature, and conveniently for most of the time, except for the very, very short period after when the molecules are first released, the deviation of this approximation is usually less than 2% if the radius of the receiver is less than 15% of the distance between the transmitter and receiver. So basically, if you're far enough away, you don't have to care about integrating over the volume of the receiver. Results from these expressions. So if we were to plot this number of molecules over time, we'll get this curve, which I introduced it earlier without really describing what it was for, but this is the curve for the expected 3D point-to-point diffusion, or really point to volume. I can't recall whether this curve was actually generated from the integral over the receiver or assuming that the receiver was uniform. Both curves look extremely similar. But just to point out the dynamics here, initially we have nothing at the receiver since all the molecules are still at the transmitter and they have to diffuse around. Initially we get this rapid increase as the molecules start to spread, and some of them end up inside the receiver. But as they keep spreading over time, what we end up eventually is we end up with a slow decrease as the molecules diffuse away. The second example system that I want to show is going to start with the same conditions as the first system, where we have our point transmitter and our passive receiver. But this time we're going to add a uniform velocity vector v, and we're going to assume that the receiver is a fixed distance d0 from the transmitter, and we're going to assume it's along the x-axis. So the x-axis velocity component will be pushing molecules in the direction from the transmitter toward the receiver. It will of course keep pushing them, so we'll push them past the receiver as well, but just to be aware of which flow is going to be tangential with the line between transmitter and receiver. We're also going to add first order degradation, so we're going to assume that our molecules, if we label them as A, that these degrade according to reaction rate K and become an empty set, and that this reaction can occur anywhere where the molecules are propagating, including while they're passing through the receiver. But there are no receiver-specific reactions in this case. So now for the analysis, we have a new differential equation. So we start with fixed second law, but now we need to include a component for the flow. We also need to include a component for the first order degradation reaction. And we can tell here that this reaction is the one that consumes our molecule of interest, because we have a minus sign here, and then the degradation of this molecule is our concentration scaled by the rate that's associated with that reaction. It's possible to show that the point concentration then that solves this system with the boundary conditions that we've defined becomes this expression here, where we have actually the same term in front that we had previously, and now our exponent has a reaction term right here, and we also have then a more elaborate terms of the distance, just the distance squared. We have along the dimension of distance, this is affected by the flow along the x direction, and then we have two other flow components, Vy and Vz, and all three of these flow components describe our uniform fluid velocity. This degradation rate K that we described as first order can also be used to approximate enzymatic degradation. And we can also then take similar approaches to what I showed earlier for taking this point concentration and determining the number of molecules that are found over the receiver volume. But as these kinds of expressions get more elaborate, they tend to favor even more and more just assuming, if you can, that the receiver concentration is uniform and scaling this by the volume of your receiver. But just to be aware that is an approximation, and the sensitivity of this approximation can be even greater because of the flow that's present. Then the flow could be helping to carry molecules into the receiver even faster than normal, so you might need to have an even stricter condition of how far away the receiver has to be in order to assume that you can use a uniform concentration assumption. So some results for this variant. In this curve on the left, we're considering just the degradation, and for the baseline we have our solid line. This is no degradation case, and then we have a case where we define some degradation rate that's greater than 0. In both of these curves we're assuming that there is no flow, and we can see that the degradation does have an impact on the peak. So the highest amount of signal is definitely decreased, but then we also get a decrease for later times as well, and the relative degradation for the peak is much less than the degradation that we can get much later. So if you're trying to design a reliable communication channel for a molecular signal, and you don't want to put too much complexity in your transceiver design, if you have a mechanism that's able to break down the signal, then that can be used. That's effectively changing the channel in order to improve a communication capability, which is an interesting approach, and this has enabled something that's possible when looking at molecular communication systems. In the second curve here, we now have flow only, so we've set the degradation rate equal to 0. We consider flow towards the receiver, so we're assuming that the y and z components of the flow are 0, and we're only tuning the x component. So compared to our baseline, we obviously have that if we increase, if we have a flow towards the receiver, we'll have a higher peak, but then of course the molecules continue to get pushed away, so eventually we'll have this signal will be weaker than the one in the baseline no flow case. We can have a flow that is perpendicular to the receiver, so in this case we have the flow Vx equal to 0, and we have one of the either Vy or Vz being non-zero. We're still able to observe a peak as long as this flow is not too strong, but then we do get a very fast irradiation afterwards. So this can be used for clearing up the channel very quickly. Some other important results I'd like to draw your attention to. One is having an impulsive point transmitter, as we did in the other cases, but instead of having a passive receiver, we can have an absorbing spherical receiver. So this is a receiver that consumes any molecule that enters within it, and then it removes them from being able to diffuse. So these molecules basically accumulate over time. And we can write the number of molecules in this case using this expression, where we have the complementary error function, which is 1 minus the error function. And this is an accumulative expression. So the number of molecules that get absorbed is non-decreasing. Another interesting result that's also non-decreasing is when you have a point transmitter as a passive receiver, but instead of an impulsive release, we have a continuous release. So we have a rate r of molecules per second being released by the transmitter. Then we can use this expression that also includes a complementary error function to describe the number of molecules that would be absorbed by the receiver. So those are just some more examples of closed form results on the number of molecules that you can get at a receiver in a diffusion-based molecular communication system. So this brings us to the end of part 1. So we've seen how differential equations enable a deterministic channel model. We've seen how we can readily represent diffusion, flow, and different orders of chemical reactions. And we saw some examples of solving the system to give us the channel impulse response. So for part 2 of this talk, we're going to transition now to a stochastic representation. And this part of the talk is shorter than part 1, but I think it's quite important because it provides the transition we need to start talking about simulations. So just to motivate a stochastic representation, all the results that I showed in part 1, these results from deterministic systems, these give us expected system behavior. However, in practice, and especially at micro scale, there can be significant deviations from these expected results. As we talked about earlier, diffusion can be modeled as a random walk. This means that there's inherently an uncertainty, assuming you don't have knowledge of all the individual solvent molecules to actually work out the precise trajectory of a molecule of interest. You have a random walk. The first order reactions, for them to occur, they need to have the correct local conditions in terms of energy of the kinetics associated with the molecule, and potentially other environmental conditions like a certain temperature and so on. Second order reactions, they require actual collisions between molecules in order for them to take place. So a receptor has to bind with a molecule sort of at the right angle and with the right energy and with the right speed in order for the second order reaction to actually occur. So all of these dynamics have an inherent uncertainty associated with them, even though we can describe them kind of at a sufficiently large scale with a deterministic approach. What is still quite useful, though, is that we can make use of the deterministic derivations. So it wasn't, if we want to consider a noisy system, it's still good that we went through the deterministic mathematical analysis, particularly with coming up with closed form expressions, but even the differential equations themselves can also be used to inform simulation algorithms. So the objectives in this part of the talk is to work towards a statistical description of reaction diffusion. We're going to see that the deterministic results from part 1, they describe the corresponding probability distributions. That is still quite handy. I will also be describing several random variable distributions that are used and that are most relevant for looking at the statistics of a molecular communication system. So we'll start with the channel response. So we'll recall this result from a few slides ago for our 3D point-to-point impulse response, where we had this point concentration. It's a function of the number of molecules transmitted, the diffusion coefficient d, our position relative to where the molecules were released, as well as the time since those molecules were released. So this expression gives us a point concentration over all space and all time greater than 0, or time greater than whenever the molecules were transmitted. You just have to shift the time accordingly. Typically, when we see these kinds of results, this result and other impulse responses, what we usually do is when we plot it, we fix the location and we vary the time. So in this figure here, which we also saw in part 1, where we have as a function of time, we're measuring the number of molecules at a receiver, since obviously our receiver is our place of interest, so we don't necessarily care what happens everywhere else. But what's actually useful to think about is flipping this a bit, so actually thinking about the channel response as a spatial PDF. So instead of fixing the distance and varying the time, consider fixing the time and varying the distance. Furthermore, in the case where we just have one molecule present. What we are able to do then is look at, we see here 3 different figures for 3 different values of time. And what we've done is we have plotted the point concentration over space. So when the molecules are first released, we effectively have an impulse at our transmitter, or distance 0. And then as time increases, we have this bell curve that gets wider and wider, showing the kind of the spread of a molecule. So if we look at something like the time minus 0.5 here, at time 0.02, we have a small value here. At time 0.05, this point has actually increased a little bit. And then by time 0.1, it has decreased again. So we can sort of map the results from many curves like this one, provide slices that we can take to put together the point concentration at a given position with respect to time. More interesting, if we were to integrate any of these results, that might be a bit hard to appreciate or intuit from looking just at the 3 of these, since they're all plotted on the same scale. But integrating these curves over all space will give a value of 1, or less than 1 if you also introduce a degradation factor. The most important thing, though, is that for a fixed time, this point-to-point concentration actually gives us the probability density. And this is quite useful. So we can integrate over some observer space to give us the unconditional probability of being observed at that time. And that's incredibly useful. So this means that our point-to-point concentration expressions integrated over the volume that we're interested in looking at give us the probability of being observed at that time. So what we get from these deterministic results is that we actually have a time-varying PDF, and the mean associated with being observed, so the probability of being observed at some particular time will be the value of the curve at this time. And you have to scale this by the number of transmitted molecules. So for this curve here, we're still plotting by some arbitrary number of molecules. You'd have to normalize that by the molecules released so that you're just looking at it for one molecule. But the main result here is that the impulse response for one molecule gives us the time-varying probability of that molecule being at the receiver. Now, this is an unconditional probability and does not account for prior knowledge or observations. So if you knew at, say, time, at some particular time, that your molecule was inside the receiver because you've observed it, then some very short time later, it's quite possible that that molecule will be still inside that receiver. So you do need to note that these probabilities that we get from the impulse responses are unconditional. But what we can do now is summarize some relevant random variable distributions. This will help lead towards applying communication analysis. I won't be covering much actual communication analysis in that talk. That's covered, I think, quite a bit by some of the other speakers in the symposium. But this kind of gets you a bird's eye view of the relevant distributions. So what we're going to consider in the following is a single observation by a receiver. We will note that observations that are made by a passive receiver at different times, those observations can be modeled as independent if the time between observations is sufficiently long. So if you take a sample and then allow enough time that molecules that are within that receiver could diffuse in and out, then mutual information between consecutive observations will be sufficiently low that you could assume that you have independent observations. And this is not usually a problem unless you're taking a very, very large number of samples around the time of when the peak of the observation is made, given a standard diffusion wave where you have a fast peak and then a slow decay. If you have a system with irreversible reactions, though, then the observations that are made by a receiver can't be independent because the molecules can't be observed multiple times. So if you have a molecule that gets absorbed at some particular time, any later sample, that molecule will still have been absorbed. So you can't readily use the same independence assumptions, but in practice this is not a major problem when performing molecular communication analysis. It's just something to be aware of, especially if you are relying on very frequent sampling of the performance of your system. But usually if you have an irreversible reaction, you don't care about changes in observations over a short interval. You really just care about at the end of a simple interval, let's say. So you only care on the scale of how often molecules are released by the transmitter. Since you know that whenever you do take an observation, you'll be collecting information about all the reactions that previously occurred. Okay, so we'll start our discussion of random variables by assuming we have one molecule that's observed once at some time greater than 0, so sometime after that molecule was released. We've already said that the channel response associated with the release of that molecule, this gives us the probability that's observed at time t, and we're going to define this probability with parameter p. So we have a probability p that the molecule is observed, and we have a probability 1 minus p then that the molecule will not be observed. So what we have here is a random trial with a biased coin, so we can apply the Bernoulli distribution, which is fairly straightforward. So we have a coin flip. Probability p is observed, probability 1 minus p that it is not observed. This readily extends to the case where we have multiple molecules. So let's say that instead of having one molecule, we now have n molecules. And these are all released from the transmitter at the same time. And that's, at this stage, it's quite important that we're assuming these molecules are released at the same time. So, at some given time t, each of these molecules will have the same probability p of being observed. So effectively, we have n trials of a success probability p, and so this lends itself immediately to being able to describe the number of observed molecules, so the total number that we see at time t, which we describe with variable x. That follows a binomial distribution. And right here we write the binomial PDF, or I should say it's a PMF, it's probability mass function, because we have, since the distribution is discrete. But we have that our number of observed molecules x is equal to little u. The probability of having u observed will be n choose u multiplied by p to the u multiplied by 1 minus p to the n minus u. Now, the binomial distribution is not always convenient to work with, so it's useful to consider approximations of the binomial. The first one I'll mention here is the Poisson approximation. And the Poisson approximation is defined by just a mean lambda. And if we we can see here that if we have n trials and each one has a probability of success of p, then the expected number of successful trials will just be their product. So lambda is equal to n times p, and then we can just apply the Poisson PMF. So the probability that our number of observed molecules being equal to u will be equal to n times p to the power of u multiplied by e to the minus n times p, all divided by u factorial. And this is valid when the number of the number of molecules n is sufficiently large and p is sufficiently small, such that n times p is finite. I think it has to be finite and small. But yeah, even though this expression still has a factorial, which is not the greatest, there are continuous approximations of the Poisson that make it still more convenient to work with than the binomial distribution. Next, we'll cover everyone's favorite distribution, the Gaussian or normal distribution. We do note that the Poisson is still discrete. It does have a factorial in it, although there are continuous representations. What if we do want to work with a commonly found, popular, and often accurate continuous distribution? So instead of Poisson, we can also apply a Gaussian approximation of the binomial distribution. The mean of this distribution, similar to the case for Poisson, the mean mu is just equal to the product n times p. And for binomial, the Gaussian approximation variance is sigma squared is equal to np multiplied by 1 minus p. And then you'll get, you can then apply the well-known distribution of a Gaussian random variable. I will note, though, that to apply this to what is an inherently discrete behavior in terms of numbers of molecules, there's a few things you need to watch out for. One is that you need to apply continuity correction if you're looking at the cumulative distribution function. So when you're looking at the probability of having some number of molecules observed, or I should say up to some number of molecules observed. And you also need to watch out for negative values, since the Gaussian is defined over the whole real domain, so it's possible that you can end up with a prediction that a number of molecules observed, not a prediction so much as a stochastic realization that the number of molecules observed will be negative, which is obviously invalid. So there are some details to watch out for when dealing with the Gaussian, but otherwise it can often be quite accurate. In everything we've discussed so far, we've assumed that molecules are released once by the transmitter, and then we've looked at the corresponding statistics. We are often interested in multiple transmitter releases at different times. So if we have some time scale here where we divide up time into different intervals, if we have on-off keying, let's say, We can transmit molecules if there's a 1 that we want to send, and not transmit molecules if we want to send a 0. And it's possible then for every 1 that we'll have some associated impulsive molecules that's created at our transmitter. So at some later time, after there have been multiple transmissions, the molecules that have been released are going to have different underlying observation probabilities. Now, if your system is linear, then the transmissions are independent and we can use superposition. And generally, we can assume the system is linear if any reactions that happen between one of these transmitting molecules, if they have no impact on whether another molecule could react. So in other words, let's give a counterexample. Let's say you have receptors on a receiver, but you have a limited number of receptors. If a molecule binds to one of those receptors, then you have fewer receptors that are still available for reactions. So this means then that there is not independence between molecules that are propagating, so you then cannot assume linearity. Unless you have a sufficiently large number of receptors that you can assume that one of them being occupied has a negligible effect on the number of molecules available. But I just wanted to point out that you cannot always assume linearity, especially when you have chemical reactions occurring in your system. But if you can't assume linearity, then an observation at any given time is just going to be the sum of the observations associated with each of the underlying transmissions. And then because of that, we can then use the statistics of the properties of particular random variables to apply it here. So the sum of a Poisson random variables is still going to be Poisson. The sum of Gaussian random variables is still Gaussian. So you can readily aggregate the statistics and determine the PDF of the number of observed molecules you can readily still have. Now, if you were to look at this particular scenario with multiple transitions and start back from Bernoulli again and try to go through the same series of assumptions, you're going to have a problem because the underlying probabilities associated with each molecule will not be identically distributed. So there'll be a different distribution depending on when the molecules were transmitted. So if you were to start from the very beginning, statistically, with this multiple molecule release approach, what you would end up with, instead of a binomial distribution, you would end up with a Poisson binomial distribution, which is quite a bit more complicated to work with. However, in practice, in most cases, people apply a Poisson or Gaussian assumption on a single transmission and then extend that to the multi-transmission case, and then they can use that, rely on that approach for all of their statistical analysis. But just to be aware that it is possible to set up your environment such that the Poisson binomial would be readily the most accurate distribution available. For using these statistics, we can actually do quite a bit. I won't be covering that in this tutorial. There'll be lots of other talks on this subject throughout the symposium. But by having knowledge of the time-varying signal distribution, this lets us predict observed values and know what the probability of a certain prediction is. This readily extends to being able to assess communication performance if we have a particular transceiver design. And more relevant for what we're going to be using is implementing simulations, which is going to be the next part of this talk. So through part 2, we showed how deterministic results lead to a stochastic representation. We saw that the channel impulse response gives the molecule observation probability. And we also discussed the Poisson and Gaussian distributions, along with a few other relevant distributions. But Poisson and Gaussian are the most convenient for modeling the statistics of a received signal in a diffusion-based molecular communication system. Okay, we come now to part 3. This is going to be on simulation fundamentals and algorithms. So there are quite a few molecular communication simulation tools available. I'll actually be summarizing a few of them more in the next part, so the last part of the talk. But for the time being, it's enough to know that the statistical representation that we've discussed, that lends itself quite well to simulations. And it's also possible to implement simulations at different physical scales. So the objectives for this part of the talk is presenting some algorithms for simulating reaction diffusion systems. I'll be reviewing some common scales for molecular simulations. Some of this might be familiar if you've been following the other talks in this symposium, but I think it's useful to review this again. I'll be describing algorithms for simulating diffusion, flow, and chemical reactions, particularly at the microscale regime. And in the context of looking at other scales, I'll also introduce the concept of hybrid scale simulations. But my aim here is to enable anyone watching this to be able to implement a molecular simulation in any desired programming language of their choice. So the simulation scales. So depending on the physical dimensions that you're considering and the levels of activity and the numbers of molecules that are involved, there are different scales that you can use. The first one is continuous, and it's represented here, where we've taken our physical environment and we've divided it up into a grid. And each grid can have associated with it a continuous value, so an analog concentration value for all the molecules that are in the system. And this approach is continuous in the sense that the values are analog. We use the deterministic expressions, or we can even use noisy variations of those if we kind of like add a noise term within each differential equation. But finite element analysis is an example of a continuum-based approach, and it's useful when you have very, very large molecule values over the space of interest, so enough to assume that you have analog concentrations. So this continuum approach is good for very large molecule counts. If you have molecule counts that are not enormously large, let's say they're countable, then it's more useful to consider numbers of molecules instead of analog concentrations. And you can still have your division of your space into some kind of grid. It doesn't have to be squares in either of these. You could have more sophisticated shapes like tetrahedra in 3D. But for a mesoscopic approach, we count the number of molecules that are in each side of these bins here. These bins are often called subvolumes. And when the reactions occur, we just change the numbers of each type of molecule within a bin, depending on what reacts and what gets produced. And we can also still have diffusion as jumps between these bins. So we can no longer just rely on the differential equations, but we can use the differential equations to come up with predictions of when particular reactions will take place. On an even more, say, particular scale, this is if we want to actually model the individual molecules, not just the counts of number of molecules. This is the microscopic simulation, where we track the identity and the coordinates in space of every individual molecule. And we can, our molecule of interest, I should say. We're not considering every individual molecule, because we have a background solvent that we don't, we're still ignoring. But if we do want to include the background solvent, then we can go down to molecular dynamics. So here's where we actually consider the solvent molecules, such as water, if we're in some kind of aqueous solution. And we would actually track and calculate the trajectories and collisions of all of the molecules in the system, the signaling molecules of interest, as well as the solvent and any other reactants or any other molecules that are present. So here we have our four names: continuum, mesoscopic, microscopic, molecular dynamics. And this categorization is enough to categorize most, if not all, main simulation tools that are available for molecular communication systems. I'm going to focus on microscopic simulation, as that has tended to be the most popular one used, and it's arguably the easiest one to kind of pick up and start working with from scratch without having to learn a lot of particular geometry, geometric algorithms, and other tools. So to perform a microscopic simulation, there are some basic components that you need to know. You're going to need to create in your programming language of interest. You're going to need some kind of container with the coordinates of all the molecules. This could be something like a linked list or some kind of vector or array, I should say. You have a dimension for each of the dimension in your system. So if you have a 3D system, you could have, say, 3 columns and then a row for every molecule. You'll need to know your molecule properties. So you'll need to know the diffusion coefficient, the flow components, the possible reactions that can be associated with all the molecules in your system. You're going to need some mechanism for adding and removing molecules if there's any kind of reaction that can take place. So you'll need some kind of extendable instantiation of memory that you can expand or contract as needed, or initialize with some, say, possible maximum size, and then let the system run from there. You'll also need to have some kind of scheduling for when molecules are going to be added by the transmitter. So this could be done just once if you're only considering a single emission. But if you're going to have a transmitter releasing molecules multiple times, you'll need to track that somehow. And you also want to schedule when the observer at the receiver is doing its counting. So when is it observing? Quite often, or I should say, the two approaches is the receiver will either observe as often as a transmission by the transmitter, or it could observe more often. So if you're trying to take multiple samples, and that's particularly relevant if you have a passive receiver, since the molecules are coming in and going out. So you need to take frequent samples to actually be able to observe the molecules while they're there. And finally, a microscopic simulation needs to have a time step, delta t, and this will be the scale over which you'll be simulating the diffusion. You could have multiple time steps if you want to get sophisticated and associate them with different molecule types. But the simplest thing is to have a single time step that you use to drive the entire simulation. So for simulating diffusion and advection together, you can just use this pseudocode, where for each microscopic molecule, you generate a candidate displacement along each of the dimensions. So if it's a 1D, you do and you generate one random variable. If you have 3 dimensions, you generate 3 random variables. And these need to be normal random variables with a mean 0, and then the variance is going to be 2 times your diffusion coefficient multiplied by your time step. And then if you have a velocity vector, you also add a constant displacement, which will be each velocity component multiplied by the time step, and you have that along each of the dimensions that you're including in your model. You need to check the validity of your trajectory, so you need to make sure that the final coordinate for each molecule is valid. You might need to do reflections or absorbing if needed. If you just have an unbounded system with passive observers, then you don't need to include this validity check. So it's easy. If this is your first simulation, you can just ignore this step, let's say, and just assume that you have a passive unbounded system, just to try it out first. And then assuming that the trajectory is valid, or if you've updated it, like if you need to do a reflection against a wall, you just have to update your molecule coordinates. And once you've done that for all of your molecules in your system, then you go ahead and you advance the simulation time by the time step, delta t. For reactions, we need to treat each of the order of reactions a bit separately. So 0th order reactions, which just as a reminder, we just get the spontaneous creation of products. Given that we have our time step, you also need some kind of molecule generation rate, g in molecules per second. You could get this from will be the standard K for a zeroth order reaction if you multiply K by the volume where your simulation takes place. You'll note though that if your volume is infinite, if your system's unbounded, then your generation rate will also be infinite. So it can be inconvenient to be running zeroth order reactions that take place anywhere in your propagation space if your space is unbounded. But assuming it's bounded in some way, there are two approaches. The first approach is you just approximate the generation time. So every time step you just generate G times delta T molecules and you place them in the environment. So hopefully if G times delta T is sufficiently large, then you can just go ahead and create that number of molecules or rounded that amount of molecules and place them in your environment. A second approach is you can simulate exact generation times. And so within your time step, you actually move sub-steps within your time step. So within a sub-step, or to find a sub-step, you determine a time until the next molecule creation. So this will be a random creation. So the distribution of random creations will be, well, the random variable for the time between these sub-steps will be exponentially distributed. And you can get this by generating a uniform random value between 0 and 1, taking the log of that value, and a negative log divided by the generation rate g. That will give us a time little delta t until when the next molecule will be created. And then if this delta t still puts us within big delta t, then we can go ahead and place the molecule and then advance the time within the global time step by little delta t. So basically, you create a bunch of these little delta t's until their sum is greater than big delta t, and then you create that number of molecules within associated with that time step. This would give us not always the same number of molecules each time, but what it does is it enables this zeroth order reaction to proceed kind of as it should as a stochastic process. For first order reactions that are not surface reactions, because surface reactions I'll have to consider separately, we have a molecule that can take a reaction with rate K and then it leads to products. So for each microscopic molecule, we need to flip a biased coin where the rate P is, the probability P is going to be 1 minus e to the power of minus rate times the time step. And that probability, we flip a coin to determine whether a reaction occurred. So if a reaction was successful, we just replace this molecule with the products. However it is that you're managing the molecule creation in your simulation. And once you've done this for each of the microscopic molecules, you then advance the global simulation time by delta t. And it is possible to extend this approach to accommodate multiple first order reactions, but in the interest of time, I won't go through that in detail today. But if you want more information on this particular implementation or any of the others for this microscopic simulations, you can refer to the Accord simulator paper that I mentioned at the beginning of the talk. For surface reactions, just to briefly give you a list of some useful first order reactions that involve surfaces. These can include adsorption, which is a kind of sticking, desorption, which is on-sticking. So let's say you've stuck. If the reaction is reversible, you can later on-stick. There's absorption, where your molecule is kind of consumed, so it sort of disappears into the surface and is no longer available to react. You can also have membrane surfaces. So you could use this if you're actually tracking molecule behavior and trajectory on either side of the surface and it's possible for a molecule to pass through, then that would be a membrane reaction. Unfortunately for the purposes of this talk, simulating surface reactions with non-ideal rates is quite non-trivial. So I'm not going to go through the implementation details in this talk. But there is a useful approximation if you assume that you have a perfect surface reaction. So let's say you have perfect absorption. A good approximation for simulating it is to assume that the absorption always occurs if the trajectory of a diffusion of a molecule passes through the surface. So if you're checking what I mentioned before about checking the validity of your diffusion trajectory, if you find that your trajectory passed you through an absorbing surface, you can just go ahead and absorb the molecule. Now that is an approximation, so there's the treatment needs to be a little more sophisticated than that to be very accurate. But for a first pass approach, that's sufficient to kind of get you started if you're interested in simulating absorbing surfaces. Second order reactions can be, in some sense, even more sophisticated. Just as a reminder that a second order reaction has two reactants, and they combine to result in some products. In a microscopic regime, second order reactions, you need to have some kind of collision detection. And what we tend to do is if we have a binding radius, so this will be a distance where if any two reactants are within this distance after a time step, then we assume that they reacted sometime within that previous time step. Now the binding radius, unless you have some certain special cases where you have some limiting values of your reaction rates and your diffusion, the binding radius is non-trivial to compute. But what we can often do is approximate second order reactions as first order. So if we assume that one of these reactants is available in excess, we can actually remove it from consideration, assume that we have some, say, fixed background amount of that reactant, and then just check it as a first order reaction for the other reactant. Now we need to scale the reaction rate accordingly. You need to scale this reaction rate with the concentration of the reactant that you've assumed is not relevant. But this is much easier and much faster for simulation than needing to do collision checks between all the possible reactants in a large molecule population. So that was it about the microscopic approach. I'll talk briefly now about a mesoscopic approach. So as I mentioned before, in the mesoscopic regime, instead of modeling individual molecules, we have this grid of boxes that we call subvolumes. And within each box, we're counting the number of molecules that are present. So instead of tracking individual molecules and their precise coordinates, we're tracking boxes of molecules and counting the molecules per box. This has a number of trade-offs compared to microscopic. It does have much better scaling in terms of memory usage as you get really big molecule populations. Since obviously you could have very large numbers of molecules within one box, then you just need to know the number of molecules. You don't need to know individual coordinates of all of them. Although as the number of molecules increases, the time between reactions decreases. So there's the complexity in terms of scaling with system size is somewhat non-trivial. Although the mesoscopic approach also has ways of scaling and accelerating in simulation when you do get large numbers of molecules. So there's actually a spectrum between mesoscopic and continuum, where depending on the local numbers of molecules and the likelihood of a reaction occurring, you can adjust the mesoscopic simulation so that it is more continuum based and therefore very fast to calculate and simulate. But anyway, that's it about scaling. For complex reactions, if you have a lot of first and second order reactions, so let's say a signaling pathway that has a lot of different steps, a lot of different intermediates, and a large number of types of molecules, it's much easier to implement these kinds of reactions in a mesoscopic regime if they are non-surface. So the surface reaction implementation is less accurate in mesoscopic because mesoscopic inherently assumes these volumes and not surfaces. So you need to make some approximations if you want to be simulating surfaces. A microscopic regime is really easy to have an unbounded system. We just don't have to define reflections off of any kind of boundary or do boundary checks. The mesoscopic approach must be bounded because you need to define these discrete subvolumes. I suppose you could create subvolumes as you go, as they get needed. But as molecules diffuse, you would need more and more subvolumes. So the memory that would be needed would grow with the size of the system. The other point I want to make is that the mesoscopic approach, it's discrete in space, but it is continuous in time, which can be quite useful. So it's more precise over time, unlike the microscopic approach, which is discrete in time because of the time step, and continuous in space. So you get these, that's another interesting part of this trade-off of the dynamic. Now, for implementing a mesoscopic approach, a lot of this is based on an algorithm proposed by Dan Gillespie in the 1970s, when he described an algorithm for chemical reactions within one subvolume. So basically a space where all molecules are uniformly distributed. Fortunately, his algorithm readily extends to diffusion as a reaction, where you're moving between subvolumes. So it's possible to add diffusion. That's been done in a lot of simulation tools. It's also been extended to include flow. We had a paper on this a few years ago where we added flow to a mesoscopic approach. The key detail in implementation is dealing with what are called reaction propensities. So every possible reaction, whether it's an actual chemical reaction or a transition between subvolumes, it has an associated propensity, which is something like a rate. But the really nice thing about the Gillespie algorithm is that if your system is if the system is uniformly distributed, then a simulation of this algorithm will be statistically exact. So you will get if you repeat this many times, the statistics of your runs will match the actual thermodynamic statistics of the reactions themselves. So it is really, it's a really nice algorithm in that way. I won't go through all the details of the approach like I did for the microscopic regime, but just to give a summary. You basically take all your possible reactions in all your subvolumes. You figure out the propensity of each of these reactions. You can combine propensities into a total system propensity, and then use that total propensity to determine the time until the next reaction to occur. And then you advance your simulation by that amount of time. You use indexing and proportions to determine which reaction occurred, so basically which molecule reacted in what way in what subvolume. So there's just a bit of a hierarchy of organizing information. It's a bit more sophisticated. But you can determine the time of the next reaction, then you execute that reaction and update the corresponding molecule counts, so take away reactants and add products. And then you update the propensities of any molecule counts that changed. And then you basically repeat the process. So through this way you go step by step. Even though you are modeling molecule counts, a mesoscopic simulation advances in individual reactions. So the timing is precise. So you can actually end up with a lot of steps because every transition is one step of the simulation. But as I mentioned, there's a scalability here. So if a propensity is sufficiently large, you can basically you can kind of simulate multiple reactions simultaneously, and that gives you some speed up to battle some of the challenges in slow speed from mesoscopic scale simulation. An interesting idea is the notion of multi-scale modeling. So it's possible to combine these approaches. This can give us some flexibility. So if you are really interested in, let's say, being really accurate in one particular subset of your environment, you can use a simulation approach that's more accurate spatially within the region of interest, and then use less accurate approaches further away from your region of interest. So this can give you improved scalability by limiting the computational complexity, so basically focusing the computational resources where they would be most useful. And this is an approach that's already used in several popular molecular simulation platforms. Not necessarily molecular communication, but those that have been developed in the physical chemistry community, which I will talk about a few of these shortly as I finish off the talk. But for example, we can have a system where you have a mesoscopic approach taken in one area, and then a microscopic approach taken in another area. And it turns out that this hybrid of microscopic and mesoscopic has actually been somewhat popular. So quite a few open source physical chemistry platforms for molecular simulations use some variant of a micro-meso hybrid. Both of these have been they have simplified approaches for considering individual molecules. You can take advantage, but by both of these I mean the microscopic approach and the mesoscopic approach. They don't consider solvent molecules. They consider a continuum, so some kind of diffusion coefficient is associated with them. But they do have some way of tracking individual molecules, which continuum doesn't, the continuum approach. I mentioned before there's this kind of complementarity in their design. So you have discrete in time, continuous in space in micro, and then discrete in space, continuous in time, meso. So by combining the two of these, you can kind of take advantage of that duality. The limitation of hybrid approaches is when you have the interface. So you need to have transitions between microscopic and mesoscopic regimes. And because these are defined in fundamentally different ways, the accuracy at this interface is going to be limited. So if you do try to use a hybrid approach, you want to be aware that you don't have these transitions between these two regimes too close to a place of interest. So if you have a simulation where you have a microscopic region around let's say a particular receiver, you might want to increase the size of that microscopic region a bit relative to the size of the receiver so that you don't lose too much in the inaccuracy of the transitions between the two regimes. I'm not going to cover the details of this, but there have been some papers covering these hybrid approaches, and I do discuss this in some detail in the simulator paper for the Accord simulator. Okay, so that was part 3. We saw that we can implement stochastic molecular simulations at different scales. There are simple algorithms available for implementing a microscopic simulation. I went over some of those in detail. And we also introduced mesoscopic simulations, which do offer interesting trade-offs, and they can even be combined with a microscopic approach. So for the final part of my talk, I'm going to go over next steps. So in particular, just let you know about some simulation platforms that are available before I come to drawing some conclusions. So in general, what I would like people to try to take away from this talk is sort of actions that they can take. I hope that the discussion that I've presented here has encouraged you to jump into literature that's available and to be able to follow the modeling approaches that are used. You can use the statistical discussion that we've had to help you try to apply the observation statistics, and even maybe try implementing your own simulation. I hope I've kind of given enough to kind of get started in that regard. If you're not really keen on developing simulations from scratch, there are certainly lots of existing simulation platforms that are available, and I'll like to briefly go through some of those. So for generic simulators, and by generic I mean these are ones that were developed more in the more broader physical chemistry community that can be used in some way for molecular communication simulations. So there's a few continuum solvers. These are both commercial products, so you have to pay for licenses. So these include COMSOL Multiphysics as well as ANSYS. Basically these are finite element solvers. So these use the continuum approach for simulating systems. See, the approaches that are more at a mesoscale or microscale, these tend to be open source. And a few you might be interested in checking out include ERDME, which is mesoscopic, Smoldine, which is a very popular microscopic approach. There's been a lot of use cases of this. and also LAMPS, which is a molecular dynamics approach. This one has had, this one's been around for a very long time, about 30 years, and a lot of active development and a lot of modules for including a lot of different types of effects that can have an influence on molecular behavior and trajectories from a wide variety of fields, things like magnetic, magnetic and electric fields, very complex flows, etc. But it is extremely detailed, so there's a very high computational complexity for running these kinds of simulations. Specifically within the molecular communication community, there have been a number of simulators developed that are tailored for it. So some advantages of these approaches that these are designed for data transmission and generating channel statistics, which the more generic simulators were not really built to do. But all existing molecular communication simulators, as of the time of this recording, are free if they are available. So they're free to access. Most, however, are not generic solvers, so they implement very specific environments. You don't have options for all the scales. Most of those that exist focus on microscopic, though there are some that are mesoscopic. As this is a fairly new research community, these simulators don't tend to be as maturely developed, and they're not all readily accessible. So some you can read about in a paper and actually have trouble actually finding the code or being able to find something that you can actually use yourself as a software resource. I'll just quickly go through these. I won't read through all the details, but one of the simulators is BNSim, and this is it actually has multi-scale mesoscopic reaction diffusion, so it's fairly sophisticated. It was written in Java. It was focusing on modeling interactions between mobile bacteria, but I believe since the papers came out, the authors moved on to other areas, so the actual development of this simulator is inactive. N3Sim was also written in Java. It can simulate a couple of simplified molecular communication environments in a square or unbounded 3 dimensions. It is microscopic. It is also able to model collisions between diffusing molecules, which is quite useful. There's a couple of different options for receiver types. And quite nicely, there is actually a detailed user guide available and instructions for use. So the links are there for accessing this particular piece of software. MUSIM, standing for Molecular Communication, is a simulator that is entirely in MATLAB. It's actually available on the file exchange, so it's easy to find. It's fairly easy to pick up and modify the code. It does include microscopic as well as Monte Carlo simulations, where Monte Carlo is basically takes the channel statistics and then just generates the results without having to simulate the individual molecules. And so this one is freely available on the file exchange, so it's easy to download it and try it out. Accord, this will be my shameless self-plug. So Accord, which stands for Actor-Based Communication via Reaction-Diffusion. This was a sandbox simulator written in C. There is currently a C++ version in development with a project student that I'm working with right now. It's a sandbox design in the sense that you can kind of build the diffusion environment as you wish by placing these geometric shapes in an arrangement, and these shapes define where the molecules are able to move around. But you can also still have unbounded space by creating a sphere that's infinitely large. It's possible to include kind of any combination of chemical reactions, flow, reacting surfaces, membranes that molecules can pass through, data modulation, and so on. Even though it's written in C, there are MATLAB utilities for kind of previewing an environment before you simulate it, and then having videos and plots created afterwards to show where you show what was created, or see how the simulation went. There's a public website that is linked from my homepage, which I'll link to at the end, as well as a user manual that's available, that's been posted there. But the development itself is on GitHub, so you can find all the code if you're interested in all the source code, or just visit the public website to kind of access the more user-friendly documentation. Some other molecular communication simulators I'll very quickly shout out. One is BINS2 or BINS2. This is a biological nanoscale simulator. I really won't say much about it because I know that Mauro Feminella, who's one of the developers involved in this project, will be talking about this in detail later this week. So I encourage you, if you're interested, to check out that talk. I'm sure that he has much more up-to-date information than anything I might have to say about this particular simulator. Another one I want to mention is Nano NS3. This was implemented on top of the popular NS3 networking simulator software, but this was a library that enables continuum simulations of bacteria signaling. So certainly not the typical use case for NS3, but it is built on top of what is a well-known communication-centered software tool for molecular communication, or it has had molecular communication added to it, so that might be useful to check out, especially if you already have been using NS2 or NS3 in your own work. I just want to very briefly mention some open challenges. So there are several related areas to what I covered in this talk with many open problems. Obviously, since this talk was quite tutorial level, it's challenging to briefly describe what the open problems are. But a few that I'm quite interested in include mapping communication results to biological systems. And part of that can include having simulation frameworks that are sophisticated enough to recreate the key details of what happens in a biological system. This includes also using communication performance to understand decision making at a micro scale. So living cells, are operating in kind of noisy, imperfect environments. They're making decisions based on these molecular communication signals that they observe, and so they have an impact on kind of the aggregate behavior. Another interesting area is modeling channels with complex flow dynamics. I covered the very simplest case of flow in this paper. The survey that I pointed to at the beginning of this talk does go into elaborate on a few other, let's say, more general, more realistic flow models. But there's still a lot of work in capturing complex flow dynamics in a reliable channel response representation for molecular communication. Anyway, that's basically the end of my talk. To conclude, we looked at formulating diffusion-based channel models from differential equations, and we saw how to combine diffusion, flow, and chemical reactions. We saw that a deterministic description leads to a statistical representation. So we talk about different statistics that are relevant, but most usually we use Poisson or Gaussian distributions. And finally, we saw that simulations can be performed over several relevant scales, and there are lots of tools and algorithms that are readily available, especially for microscale systems, which I went through some pseudocode with. So that's the end of my talk. There's my homepage if you're interested in reading more about my work or about the simulator tool that I developed and have in development. I'm happy to address your questions in the Q&A time if I haven't had that already. And thank you very much for all of your time for this seminar today and for your attention. Thanks.